All right, so I'm sitting here in office hours. I figured I'd record another one. And so here we go. So 9.4, effusion and diffusion of gas molecules. So far we've looked at pressure, temperature, volume, mole relationships. One increases, the other decreases, inversely proportional, all of that stuff. Then we looked at stoichiometry and partial pressures. Now we're going to look at the motion of gases. Okay, so there are two terms that we're going to be interested in. The one that we're really interested in the most is molecular effusion, the escape of gas molecules through a tiny hole. It's something that you actually see problems on pretty often. But let's take a look at the idea of diffusion versus effusion. So diffusion is simply having a partition and then moving the partition away and seeing how quickly those things blend together, how quickly gases blend together. And generally what you're going to see is different size gas molecules. So if I have a mixture of different size gas molecules, the question is, how quickly do these things diffuse? How do they move into the open space? Okay, so that is diffusion. If it's things are not as limited as effusion. So effusion is, here I have a container, and instead of the partition being completely solid, I have this tiny little hole here. And what we should think about this tiny little hole here, it's a different color maybe, there we go. This tiny little hole here can move one molecule at a time, can actually go through there. So in that, you're going to see one molecule at a time. So the thing is, how quickly can things effuse based on their size? So if I have a bunch of the blue ones happen to be small, and I happen to have these large red ones, let's say, it has to do with size and ultimately speed. How quickly does the effusion occur? And what we find out is these smaller ones tend to make it through first, the smaller, because they're moving a lot quicker. So one particle at a time versus everything going all at once. Speed has a lot to do with it. So again, diffusion versus effusion. Diffusion is essentially how quickly gases will fill the void, how quickly they'll fill the space, the new space that's available. And then effusion is very specific to how quickly can we basically put things through a small pinhole. Pinhole transfer of gas. So if you fill a balloon with air and you fill a balloon with helium and you fill them to the same exact size, so they have the same volume, they have the same number of moles of gases. In air, you are going to have, in fact, we can kind of do a quick view of this. So if I have two balloons, so here is my first balloon that is filled with helium. And I have a second balloon that is about the same size that is filled with oxygen, filled with air. So we've got what, O2 and N2 mostly. Over time, what do we expect to happen? Well, what we know happens is these balloons do get smaller. But the question is, which one gets smaller quicker? Turns out helium gets much smaller quicker because it can effuse through the holes in the plastic. Helium is tiny. Helium is very small, and it can actually make it through the rubber, the molecular net that is rubber being held together. So if you imagine the wall of this, what it actually looks like is something like that, because helium molecules, being very small, can actually effuse through. It takes oxygen and nitrogen a much larger amount of time to do that, because although the rubber is the exact same, the molecules are substantially bigger. So they're moving slower, and they're not going to have as many opportunities to leave as the helium is. I know it's very strange, but that is absolutely a thing. It's weird to think that you have this thing sealed and somehow it's losing gas, but it totally is. It's not like the gas is just disappearing. Much like if someone says, oh, we have helium in these windows, like in the double layer between, doesn't mean anything. The helium effuses very rapidly. It doesn't help you at all. Never buy anything with vacuum or helium, because it's just the gas is gonna effuse in or out. You're never going to, it's not worth the money. So the equation that we're interested in, and this is Graham's law. Graham's law is basically going to look at the rate of effusion of A over the rate of effusion of B is equivalent to the molar mass. That is the symbol that we typically use for molar mass. Rate of effusion of A over the rate of effusion of B is equal to the square root of the mass of A over the mass of B. Okay. Okay. Yeah, I just want to check on that. I actually think I might have that backwards, because I think it's supposed to be upside down. So 1 second. Yes. As I thought, I do have this backwards. So this actually should be B on top and A on the bottom. I'll try to fix that on your, but yeah, rate of effusion of B over the rate of effusion of A. There we go. So they should be, essentially, they just have to be crossed across one another. Okay. So typically what you see here is this is a ratio. So if this ratio happens, you end up with a number, for example, because you plug in the molar masses and you end up with a number of 3.5. Essentially what that is saying is, as an example, I should say, as an example, if we end up with a ratio of 3.5 as our answer, that is simply saying that gas A effuses 3.5 times faster than B. So essentially it's saying it's going to leave 3.5 times faster than B. So if I had A and B in a balloon and they started with equal amounts, 3.5, I would lose A 3.5 times faster than I would lose B. Okay. All right. So the typical thing that we're looking at is speed. Okay. What we're going to notice here is down on the x-axis, I have velocity in meters per second at 298, so at room temperature, and I have the relative number of molecules on the left-hand side. And what you notice is, first of all, it's very, very upright. Okay, so it's very condensed at the top. This is not a bell curve, by the way. What you are going to notice is this is not a bell curve. These things are going to be a little bit longer on the right-hand side. So large molecules look like this, and small molecules look like this, as in they have a much larger percentage of them moving very fast. So if you look at helium, for example, helium has a bunch, the average speed is way up here. So it's moving or hydrogen, I should say, hydrogen is moving much faster than the average krypton is. Okay. So again, the peak is not the average. Yes, it is the largest percentage, but because it's a little bit skewed on this side, there's a few more over here. The average speed is a little bit beyond the highest point. Okay. So ultimately, what does this mean? Lower molar mass equals a faster speed on average. Okay. Some are moving. I mean, we have quite a few that are moving very slow, but we have a ton of hydrogen that's moving fast and very few nitrogen molecules that are moving fast, or any of the others. Okay. So smaller that is, the faster it goes, which kind of makes sense. So what that also means is small molecules are going to effuse faster than than large molecules. So how much faster does hydrogen effuse than helium? So I'm going to show you how this works, and then I'm going to let you kind of work through the others. So here we have rate. Again, it's going to be rate of, and I'm going to put some real ones, hydrogen gas. How much faster does hydrogen effuse than helium versus rate of helium? So how it's set up right now, it's the rate of hydrogen gas over the rate of helium. So how many times faster is hydrogen than helium, which is the right way to set it up. We're going to do the square root of the molar mass of hydrogen on the bottom and the square root of the molar mass. By the way, we could just simply say square root of all of them too. We don't need to do the square root of helium on the top. So the rate of effusion of both of these, let's figure it out. We plug in some numbers. So the molar mass of hydrogen is 2, and then the molar mass of helium is 4. Okay, and so now we simply, I just want to make sure that the helium is right. That's exactly what I need to be. Okay. Yeah, now 4 is close enough. 1.41 is going to be our value. Sure. What this means, again, is hydrogen effuses 1.41 times faster than helium. That is the end result of our calculation. So an unknown gas diffuses 1.19 times faster. So what we have here is, that's my ratio. And now you have to set it up correct, because here is my argon. So I'm going to use molar mass of argon from this, and I'm going to have the molar mass of the unknown. So the question is, what is the gas weigh? What is it? Okay, remember, our gases can be generally, the things in gaseous form are going to be the noble gases, or nitrogen, oxygen, or I guess I should say X, the halogens, right? X2. And in fact, not even the halogens, just fluorine and chlorine. And then we have the noble gases, helium, neon, argon, krypton, xenon, radon. There we go. Yeah, so what is the unknown gas? Again, molar mass. Make sure if it's a diatom, you're taking it as a diatom. And then this one, this is actually a really good question. Gaseous ammonia and gaseous HCl are on opposite ends of the 50 centimeter glass tube. When they react, you're going to get a white precipitate forms. So essentially what happens is when you combine these two things together, HCl plus NH3, you end up with NH4Cl, which is a solid. So the question is, which side, how far? Let's just say that it's closer to this end. I'm not telling you that it is it or it isn't, but let's say it's there. What is the distance between that and that? Okay, there is some math you have to do here. It's actually a really cool little problem. So give that one a go. All right, so that is the end of that. We're going to take a look at kinetic molecular theory, which we kind of briefly looked at in the last one, but